Okay, so here we go again. Another problem on superposition. Find the support reaction to the shaft shown using superposition and a compatibility condition. This is the main part here. Assume W is equal to 50 pounds per inch. This W up here kind of looks like an omega, but it's W. And then A is 30 inches and L is 100 inches. Okay, so I'm going to go ahead and set this up. If you go ahead and do this, I'm actually going to redraw this the opposite direction as a free body diagram. If you draw it like this, it's a little bit easier. I kind of like it from the left to right as opposed to right to left. It makes the equations easier a little later on. Okay, so we've got this thing going on like this, distributed load, and then we also have this spot right here with a reaction. We're going to call it RB. And we've got a reaction back here of RC, and then we're going to have a moment of, I'm going to call that MC, and then that's about it. Okay, so we know that the distance is 70 inches in here, 70 inches right there, and then 30 inches right here, just like that. Okay, so if we do the sum of the forces for this setup, we're going to do the sum of the forces in Y is equal to negative 50 lb per inch times 100 inches. This is the entire distributed load plus RB plus RC. So we've got the sum of the forces in the Y direction. We're going to say this is X, this is Y, just like that. Okay, so as you can see here, right now we've got two forces. We're going to go ahead and do the sum of the moments about C. We're going to call this point C over here. Some of the moments about there, so we've got equals negative 50 lb per inch times 100 inches. Now this is a tricky little part about distributed loads. When you're doing the moments, you can actually combine this load and put a single large load mass, we're going to call this big W, underline it, which is the entire load focused at the halfway point of the distributed load. And that's how you can calculate the moment, because that's how it all ends up working out. So in this case, we're going to take, since it's over the entire length, we're going to take the entire length of the distributed load and divide it by 2, which puts it in the middle. So we've got 50 pounds times 100, which gives us the magnitude of the load, and then this is the location, which is 50. And so then we do plus RB times 70 plus M, the MC over here. It's a little hard to see, but MC plus MC, so this M. So if you look at that, you see we have 1, 2, 3 variables, but we only have 2 equations. So we're going to have to use something to solve for the get a third equation. So what we're going to do is we were told to use superposition with a compatibility condition. So that's what we're going to do. So redrawing this free body diagram, if you're looking in the back of your book, we use the Shigley book ME for machine design, machine analysis and design by Shigley. And what you do, if you look in Appendix 9, you'll see a picture that kind of looks like this, of a cantilevered beam with a force on it. And what we're going to do is we're going to call this this is the reaction force, we're going to call this FC1, and then M1, and then we're going to have FB. I'm using slightly different variable names this time around, just so we can differentiate between this chart and this chart here. Okay, but this is all the same. The same distances apply all the way through here. So, if you're looking at the back of your book, you'll see that what we're going to use is the displacement equations from the superposition principles in the back of the book. And that equation is YB is equal to, I'm actually going to call this YAB, change that to AB, because we're going to have to do this twice at the same location, is equal to negative fx squared all over 6 EI of x minus 3a. Where a is the 70, this is a right here, this is the distance a over here, which is going to be equal to 70. X is the distance from the axis where the force is acting, so if we have x going this direction, x will equal that distance there as well, until force. And then 3, I think that covers just about everything. How's that focusing? Oh yeah, I think you can see that. Okay, so moving on here. So if we calculate that out, we'll find that YAB is equal to 1 point, hang on, I apologize. I have to double check my solution here to make sure I'm giving you the right stuff. Okay. Over EI. Okay. Okay. This is going to equal 1.143 times 10 to the 5th over EI. So we, oh, sorry. Over EI. So as you can see here, EI, we can't solve for EI. I don't think you guys can see that. There we go. So EI we can't solve for because we don't have the diameter of the shaft or even what material it is. I don't think we're even told that in the problem. But that's okay because that's going to remain, that's going to cancel out a little later. So moving on to the next situation, for the distributed load, this was the reaction due to this little pin here holding it up. So we solve for that reaction what the displacement would normally be. And then, if we go over and we do the distributed load like this, just like this, we'll end up with a moment acting in this direction, opposite to the, well, this is assumed, but we can assume opposite to that direction because this is going to create a moment like this, so we need a moment reacting to it like that. And I'm going to draw a little line here to split at 70. And I'll explain that in a minute. So what we're going to do is we're going to use another equation from Appendix A9, where you have a distributed load, a cantilever distributed load. YB, the displacement at B. We want to do the displacement at B because this is going to be important in our compatibility equation. Because we know that at this point, the displacement is going to be 0. So we want the displacement at B from this distributed load. So is equal to YAB2. I'm going to call it 2 to distinguish from that one. And then we've got WX squared all over 24 EI of 4 LX minus X squared minus 6 L squared. And if you solve that all out, you'll end up with YAB2 is equal to excuse me, negative 3.767 all over EI. So solving that all out, and L again is the distance from here, or L is the total distance of the bar. Make sure I'm telling you the right stuff here, yes. L is the total distance of the bar, so 100. X is the distance to the force, or to the point where we're splitting off. Because we're basically ignoring this little chunk of ground. Yeah, I'll just work it out for you. I'll show you the numbers here. So the numbers down here is 50, which is the distributed load, times 70 squared, which is the X up to this line, all over 24 EI, times 4 times 100, which is total length, times X again, 70, minus 70 squared, X squared. I'm going to have to carry off down here again, so continuing, I'm sorry, times minus 6 times 100 squared. Now, you may, in this, we have the distributed load, which is pretty easy, so there's nothing too tricky about that, but it's mainly the split right here, and realizing that when you're using this force in this equation, X is equal to the place right here, because within that equation, you have to define X at the point where you want to know where the displacement is, especially for these distributed loads. So we want to know the displacement at this line, so we make X 70. If we wanted to know the displacement at the end, then we'd make X 100. Okay, so you've got this value and this value. So, taking those, we need a compatibility equation. And like I said, we picked this spot and this spot because that's where the reaction is, and we know this bar doesn't displace right here. So we imagined, we superimposed the forces on that spot to see how it would displace if that bar wasn't there, how it would displace if that force from the bar was there and this force was gone. So we find out that Y YAAB plus YAB2 should equal 0 in order to have this be a static problem. Because if it's not equal to 0, then you have it all shooting up, or it's collapsing, or something else. So these two have to equal to 0, so the displacement, so that the bar doesn't move, and keep it a static problem. So if you go ahead and calculate that by subbing in YAB and YA2 equal to 0, you'll find out that, since YAB2 is equal to that, you got 1.143. Oh, I apologize. This is also times 10 to the 8. Times 10 to the 8. I'm sorry. And double check my other, yes, times 10 to the 8 right here. But anyway, 1.143 times 10 to the 5th over the I is equal to 3.767 times 10 to the 8th over the I. And from this, you can see that these two will cancel. Oh, excuse me. I took that one step too far. Hang on. I forgot one thing. Up here, I'm skipping steps too much. Up here we have f times x squared. We actually don't know what f is, so that f goes in right here. F times 1 times 0.30. There we go. So then this is FB. You've got FB right here, right there. Then you solve for FB, and then you'll find out that it is actually equal to 3. FB will equal 3.29 KSI or KPIP, whatever kind of notation you want to use on that. But this, and then from this, you can put it back up into your original equations as the reaction at B, and then solve for RC and M. So that's how you use superposition in order to find the reactions of something.